This is part 2 of Chapter 9 Practice Problems. I believe we left off with part B in example 9.7, so we'll pick up with part C. This has two half reactions that are as follows, and let's peek back at the question first. It says, predict which of the following reactions will occur, and for those that will occur, balance the equation and indicate which element is oxidized and which is reduced. So for part C, we have tin solid plus hydroiodic acid, and then what does that produce? So our two half reactions, so for the oxidation, we go from tin to tin, tin to, I was going to make a bad joke, never mind. And so we lose electrons there, so lose electrons oxidation. And for the reduction, we have our H+, that is gaining electrons to go to the neutral hydrogen gas. If we add the two half reactions together and then cancel out the electron parts, which are the two electrons, we'll get this reaction. So we have our tin, the two protons, our tin2, and hydrogen gas. Our overall balanced molecular equation would be if we added in the nonmetal ionic parts for our two charged pieces. So we have tin plus hydroiodic acid, and then the tin to iodide and hydrogen gas. Tin is going to be oxidized. It goes from 0 to +2, and the hydrogen is reduced, going from +1 to 0. Notice we did have to have some balancing with the 2. And you can see that here, so that we have 2 electrons on the reactant side and 2 electrons on the product side. Reactions in which the hydrogen ion is reduced to hydrogen gas are known as specifically hydrogen displacement reactions. Again, one thing to remember is to check your conclusions by working each problem backward. Write each equation in reverse and compare the position of the elements in the activity series. Another thing that you can do is just to make sure that these electrons cancel out and that everything makes sense and that you have balanced elements on both sides. Whoops. Here we go. Alright, let's take a look at example 9.8. Just read along with me. For an aqueous solution of glucose, C6H12O6, determine A, the molarity of 2 liters of a solution that contains 50 grams of glucose. Part B, the volume of this solution that would contain 0.250 moles of glucose. In part C, the number of moles of glucose in half a liter of this solution. So our strategy here is going to be to convert the mass of glucose to moles, and then use the equations for converting of molarity, liters, and moles to ultimately calculate our answers. So our moles of glucose we can find by taking the mass that's given, which is 50 grams, which is shown here, and then the molecular weight of glucose. That would be 6 carbons, 12 hydrogens, and 6 oxygens. You take the atomic weight of carbon times 6, hydrogen times 12, oxygen times 6, add all that together. You should get something like 180.2. We do this math operation, the grams cancel, and it leaves us with moles. So we have 0.277 moles of glucose from this mass. So for part A, we're asked to calculate the molarity of a 2-liter solution. Molarity relates moles divided by liters. So we can take our moles, 0.277, and then divide by the liters that it gives, divided by 2, and we get 0.139. The unit for molarity is in uppercase M. For part B, we're asked to calculate the volume of this solution that would contain 0.250 moles of glucose. So we can use the calculated molarity, and instead of the 0.277, we're going to use 0.250, which is what is stated in part B. So 0.250 moles, and we're dividing by molarity, which is moles per liter. The moles will cancel, and that leaves you with liters. So you get 1.80 liters. The last one, we're asked to calculate the number of moles of glucose in half a liter of this solution. So in half a liter, we can take, and I believe it's the solution from part B, so I think it continues on. So we use half a liter, and then we use this molarity, 0.139, multiply here. Liters times moles per liter, the liters will cancel, leaves us with moles, and we get 0.0695 moles. So if you're pretty good with calculating grams to moles or moles to grams using molecular weight, then this won't be any different with the idea of going from molarity to liters or molarity to moles and so forth. Remember that we can check to see that the magnitude of our answers makes sense. For example, the mass given in the problem corresponds to 0.277 moles of solute. If you are asked, as in part B, for the volume that contains a number of moles that's smaller, make sure that your answer is smaller than the original volume. Example 9.9. What volume of 12 molar hydrochloric acid, a common laboratory stock solution, must be used to prepare 250 milliliters of 0.125 molar hydrochloric acid? Our strategy here is going to use the dilution equation. The dilution equation, I usually write it as M1V1 equals M2V2. Let me get a little drawing tool here. M1 V1 equals M2 V2. M1 is my initial, V1 is my initial, M2 is my final, V2 is my final. Also, M1 will be my concentrated or my stock. This will be how much stock do I need. And then M2 is our diluted molarity, and V2 is our total diluted volume. So it says, what volume of 12 molar hydrochloric acid must be used to prepare 250 milliliters of 0.125 molar hydrochloric acid? This is the most common that you'll see in a lab, is you'll take a concentrated solution and then you'll need to make some amount of a less concentrated. So our concentrated volume, or stock volume, is 12 molar. That would be M1. Our M2 is the new diluted, which is 0.125, which is here. The final volume is 250 milliliters, which is V2. So we need to calculate for V1. So if we divide both sides by M1, we would get V1 equals M2V2 over M1. And let me just write that. So we get V1 equals M2 V2 over M1. And that's what's shown here. So here's our V1. Our M2 is 0.125. Our V2 is 250. And our M1 is 12 molar. And we do the math here. The molarity cancels, and then we're left with a volume of 2.60 milliliters. So what that would mean is that we would take 2.6 milliliters of the concentrated 12 molar hydrochloric acid, and then we'd fill the rest up until we hit 250 with water, and then we'd get 250 milliliters of this less concentrated solution. We can plug the answer into equation 9.4 and make sure that the product of concentration and volume on both sides of the equation give the same result. So then once we have our answer, our V1, we could multiply these two and make sure that they equal these two. And let's clear all that out. 9.10. Starting with a 2 molar stock solution of hydrochloric acid, 4 standard solutions 1, 2, 3, and 4 are prepared by sequential diluting 10 milliliters of each solution to 250 milliliters. Determine A, the concentrations of all 4 standard solutions, and B, the number of moles of hydrochloric acid in each solution. Again, we'll use our dilution equation, and this has been rearranged so that we have our M1 V1 over V2, if you're using the way I wrote it on the last slide. And this would be our M2. They use C and D. C would be concentrated, D is dilute. So just another way that we can write it. Part B, we want to know moles, which we can determine by taking molarity times liter. So moles over liters times liters. Liters cancel, gives us molarity. And then another thing is just showing 250 milliliters is the same thing as saying 2.5 times 10 to the negative 1 liters, or 0.250 liters. So using this general formula for 1, 2, 3, and 4, we'll take our 2 molar stock, and we have 10 milliliters of it, and then we dilute that up to 250 milliliters. So then that changes the concentration from 2 molar to 8 times 10 to the negative 2 molar. So then we take this diluted solution, 10 milliliters of that, fill that up to 250 of water, and we will get 3.2 times 10 to the negative 3 molar. Then we take this one, 10 milliliters of it, and then fill that up to a total of 250. And we get this value, 1.28 times 10 to the negative 4. And then we do that again. We take 10 milliliters, fill it up to 250, and then get much less concentrated. So what we can do, and I'm going to draw something, and I'm doing this with a mouse, so it's probably not going to look very good, but we'll use this volumetric flask. I think this is the noise you have to make when you draw it. There it goes. And it's scored with a line on it. So this would be like a 250 milliliter volumetric flask. So for each of these, we can picture what we're doing here. I'm going to just take our stock solution of hydrochloric acid. It's not blue, or it'd be magical, I guess. So we take 10 milliliters of 2 molar, and you measure that out, and you put that in the bottom. There it is. Takes a little while to fill it up, doesn't it? All right. So then, when we get to this line, that would be a total of 250. So we've added in 10 milliliters of our concentrated, and then we're going to add in water. Water's blue as well. We'll just fill it all the way up to that line. Not very good at coloring with a mouse, but I think you get the idea. And we mix it together so that it looks nice and even. And then this would be our diluted. So then you could take 10 milliliters of this, get a new 250 milliliter flask. So just like I did a moment ago, you fill that in the bottom, and then you'll fill the rest up with distilled water. So what you're really doing is you're taking 10 milliliters of a solution, and then 240 of water to get a total of 250. And then you get a new concentration, and then you just repeat that 4 times. So hopefully you can wrap your mind around that. Part B, we want to figure out how many moles we have. So you can take the concentration from each. So here's our 4 concentrations. And then you're going to multiply by 250 milliliters. So that'd be 0.250 liters, or as they wrote it here, and you barely even need scientific notation, but they did it anyway, 2.5 times 10 to the negative 1. The moles the liters cancel, and then it leaves us with moles. So we have 2 times 10 to the negative 2, 8 times 10 to the negative 4, 3.2 times 10 to the negative 5, 1.28 times 10 to the negative 6. Okay. Next example, 9.11, using square bracket notation. Express the concentration of A, chloride ion in a solution that is 1.02 molar in aluminum chloride. B, nitrate ion in a solution that is 0.451 molar in calcium nitrate. And C, sodium carbonate in a solution in which the sodium ion concentration is 0.124 molar. One thing about this square bracket notation is that when you put brackets around anything like they've done here, that just represents that it is representing a concentration, and then a synonym of that is molarity. So if we just said this is 0.124 without even having this M there, then you would know it is the concentration. So it's a notation used for concentration. Our strategy is use the concentration given in each case and the stoichiometry indicated in the corresponding chemical formula to determine the concentration of whatever is specified, be it ion or compound. So for part A, which is using aluminum chloride, there are 3 moles of the chloride ion for every 1 mole of aluminum chloride. So we have 1 mole of aluminum, 3 moles of chlorine. Here's our general formula of the decomposition. Aluminum chloride produces aluminum plus 3 charge and 3 parts chlorine minus. The concentration of our chloride ion will be 3 times the concentration of the aluminum chloride. So written out, concentration of chlorine is going to be equal to the concentration of aluminum chloride times 3 moles of chloride and 1 mole of aluminum chloride. So putting some numbers in here is just 1.02 times 3, and we get 3.06 molar. For part B, there's 2 moles of nitrate in every 1 mole of calcium nitrate. And here's the formula. I won't go through it again like we did for part A. So then that would mean that there's twice as much. So nitrate will be twice the concentration of the calcium nitrate. So we take 0.451 and just multiply by 2. And for the last one, there is 1 mole of sodium carbonate for every 2 moles of the sodium ion. So it will be half of the sodium ion concentration. So our sodium ion concentration is 0.124, and then that will be multiplied times 1 over 2, which is a half, and that is 0.0620 molar. And as they've written it here, if you set it up so that units will cancel, make sure that your units cancel properly. Also remember that the concentration of an ion can never be less than the concentration of its dissolved parent compound. It will always be the concentration of the parent compound times its stoichiometric subscript in the chemical formula. Continuing on to example 9.12, determine the pH of a solution at 25 degrees Celsius in which the hydronium ion concentration is A, 3.5 times 10 to the negative 4 molar, B, 1.7 times 10 to the negative 7 molar, and C, 8.8 times 10 to the negative 11 molar. Strategy is, given the hydronium concentration, we can use a formula which relates pH to hydronium. It's defined that pH, which is the power of hydrogen, is equal to the negative log of the hydronium concentration. So we just plug and chug this right into a calculator. Part A, pH equals negative log of that given concentration. We get 3.46. For part B, plugging that in, we get 6.77. And part C, we get 10.06. When a hydronium ion concentration falls between 2 quote-unquote benchmark concentrations in table 16.4, the pH falls between the 2 corresponding pH values. In part C, for example, the hydronium ion concentration, which is 8.8 times 10 to the negative 11 molar, is greater than 1.0 times 10 to the negative 11 molar, but less than 1.0 times 10 to the negative 10 molar. Therefore, we expect the pH to be between 11 and 10. Example 9.13. Calculate the hydronium ion concentration in a solution at room temperature, 25 degrees Celsius, in which the pH is, and it gives these three values, 4.76, 11.95, and 8.01. This is called taking the anti-log. This is where you get power of hydrogen, so it's raised to an exponent. So to do the anti-log, you just raise it to the pH, and these are all base 10 logs. So we are going to use 10 here always. So given a pH, our hydronium ion concentration is equal to 10 raised to the power of the negative whatever the pH value is. So same thing, we just have to plug these in. I'll go through the first one and then just read the answers for the next two. For part A, it's 10 raised to the power of negative 4.76, and we get back our hydronium concentration, 1.7 times 10 to the negative 5 molar. If you would take the negative log of this value, you'd get back the pH, which is 4.76. So 9.12 and 9.13 are showing you the reverse, or the forward and the reverse. Going from concentration to pH, and then going from pH to concentration. And the answers for part B and C are 1.1 times 10 to the negative 12, 9.8 times 10 to the negative 9. If you use the calculated hydronium ion concentrations to recalculate pH, you will get numbers slightly different from those given in the problem. In part A, for example, negative log of that is 4.77. The small difference between this, it comes from significant figures, is due to a rounding error. Remember that a concentration derived from a pH with 2 digits to the right of a decimal point can have only 2 significant figures. Also note that the benchmarks can be used equally well in the circumstance. A pH between 4 and 5 corresponds to a hydronium ion concentration between 1.7 times 10 to the negative 4 and 1.0 times 10 to the negative 5. Moving on to example 9.14. A 0.8633 gram sample of an ionic compound containing chloride ions and an unknown metal cation is dissolved in water and treated with an excess of silver nitrate. If 1.5615 grams of silver chloride precipitate forms, what is the percent by mass of chlorine in the original sample? Strategy here is using the mass of silver chloride precipitate and the percent composition of silver chloride, determine what mass of chloride the precipitate contains. The chloride in the precipitate was originally in the unknown compound. Using the mass of chloride and the mass of the original sample, determine the percent chlorine in the compound. So our setup here, we can determine the percent chlorine in silver chloride by dividing by the molar mass of chlorine, by taking the molar mass of chlorine and the molar mass of silver chloride, which is shown here. In the numerator, 35.45 is our mass of chlorine, and 35.45 again, mass of chlorine. This would be mass of silver. So both of those together is total molecular weight of silver chloride. So percent of silver, or percent of chlorine in silver chloride is 24.72%. The mass of chlorine in the precipitate is 0.2472 times 1.5615. So this is just taking a percent as a multiplier. You just keep it as the fraction. 0.2472 multiplied by our total, and we get 0.3860 grams. So then we can do our percent calculation part over whole. The percent chlorine in the unknown sample is the mass of chlorine in the precipitate divided by the mass of our original. So we take what we just calculated. Let me show you that again. 0.3860 divided by 0.8633. multiply by 100, we get 44.71%. Pay very close attention to which numbers correspond to which quantities. Go back if you need to and review this one again and practice it before you continue watching. It's very easy with these type of problems to lose track of which mass is the precipitate and which is the original sample, and you don't want to flip-flop those because you'd get an incorrect result. Moving on to 9.15. This is a titration type experiment with acids and bases. In a titration experiment, a student finds that 25.49 milliliters of a sodium hydroxide solution is needed to neutralize 0.7137 grams of KHP. What is the concentration, and is just the molarity, of the sodium hydroxide solution? And they give us we need to have the chemical formula of KHP, which is here. There it is. Alright, strategy. Using the mass given in the molar mass of KHP, determine the number of moles of KHP first. Then recognize that the number of moles of sodium hydroxide in the volume given is going to be equal to the number of moles of KHP. Usually this is the case, where you find the moles of one, and then the moles of the other are the same, and then you can get back to the volume and then molarity. So then once you have the moles of KHP and NaOH, we can divide the moles of NaOH by the volume to get molarity. The molar mass of KHP, and of course they'd need to give you the formula for it, which is KHC8H4O4, and this is a type of acid. And just adding all of this up, total molecular weight is 204.2. So taking the mass in the beginning is 0.7137 grams, so that's right here. We divide by our molecular weight, and that gives us moles. The moles of KHP is equal to moles of NaOH, so that just carries on right here. And then we find our volume, 25.49 milliliters. And you remember that molarity is not moles per milliliter, but it's moles per liter. So we need to actually have this in liters. You can just divide it by 1,000 or move the decimal place if you can see that. That's 0.02549 liters. We do the math here, and we get our concentration, 0.1371 molar. Remember that molarity can also be defined as millimoles per milliliters. So moles per liter, then we could do millimoles per milliliters. We could also do micromoles per microliters. Another thing you could do is try solving the problem again using millimoles and make sure you get the same answer. So it doesn't matter, just as long as the standard is moles per liter, you could do it with millimoles per milliliters, micromoles per microliters, nanomoles per nanoliters, and so forth. Our next example, 9.16. What volume, in milliliters, of a 0.203 molar sodium hydroxide solution is needed to neutralize 25 milliliters of a 0.188 molar H2SO4 solution, that's sulfuric acid? First thing that we'll need to do is write out and balance the chemical equation. This is a type of neutralization reaction. It's a titration. And we have NaOH plus H2SO4, and it would be very similar to a double replacement. So we'll take the Na, the metal, with the non-metal part. This is the polyatomic SO4. And then we combine OH and H. Here's our neutralized part. We get water back. Aqueous, aqueous, aqueous. This is L, because it's a pure substance, pure water. When you have acid and base in equal amounts, or somewhat equal concentrations, and we get a neutral solution, you'll also get a salt as your byproduct. The base in the diprotic acid, it's diprotic meaning that it has two acidic hydrogens, so sulfuric acid is H2, so that would be diprotic. Combined in a 2-to-1 ratio. we get 2 parts of NaOH for 1 part of H2SO4, and that just comes about when you balance this with the coefficients. Use the molarity and the volume given to determine the number of millimoles of sulfuric acid. Use the number of millimoles of sulfuric acid to determine the number of millimoles of sodium hydroxide. We can use the millimoles of sodium hydroxide and the concentration given to determine the volume of sodium hydroxide that will contain the correct number of millimoles. So let's see what that looks like. So we take our concentration, 0.188, multiply by 25 milliliters, and then just peeking back at these numbers, we get, here's our 0.188 and 25 milliliters, and then here's our other concentration. So this would come out to be 4.70 millimoles. This is if we don't, this is moles per liter and milliliters. If we put this in milliliters, then we're going to get out millimoles. The millimoles of sodium hydroxide that are required, we'll take our 4.70, and then we use our coefficients. It's not 1-to-1 in this balanced reaction. So we get 2 millimoles of sodium hydroxide over 1 millimole of sulfuric acid. Millimoles of sulfuric acid cancel, so we just double this value to 9.4 for our sodium hydroxide. Our volume of 0.203 molar sodium hydroxide is then going to be, we take our millimoles of sodium hydroxide and we use the concentration. So moles per liter is the same thing as saying millimoles per milliliter, as I mentioned in that think about it a moment ago. We can arrange this so that the millimoles cancel, and then we get out a milliliter, 46.3 milliliters. I recommend coming and going through this one like another time or two, and I think you'll get it. Notice that the two concentrations, 0.203 molar and 1.88 molar, are similar, both round to the same value of 0.2. Therefore, the titration of a diprotic acid with a monobasic base of roughly equal concentration should require roughly twice as much base as the beginning volume. So we started with about 25, double that is 50. So we got 25 and 2, which gives us 46.3. So just kind of using some logic there. Last one. A 0.1216 gram sample of a monoprotic acid is dissolved in 25 milliliters of water, and the resulting solution is titrated with 0.1104 molar sodium hydroxide solution. A 12.5 milliliter volume of the base is required to neutralize the acid. Calculate the molar mass of the acid. Strategy here is because the acid is monoprotic, it'll react in a 1-to-1 ratio. 1-to-1 ratios are most common. Therefore, the number of moles of acid will be equal to the number of moles of base. The volume of base in liters is 0.0125 liters. And that's just taking this value here, dividing by 1,000. Our solution would be our moles of base, and we can do that from our volume, 0.0125 liters. It's just taking this, putting it in liters. And then we use our concentration, which is moles per liter, written out, moles per liter for molarity. We set it up in this fashion so that our moles are on top, liters on the bottom, so that liters cancel. It leaves us with moles. And then since it's 1-to-1, our moles of base are equal to moles of acid. So here's our moles of base, same as the moles of acid. We can take our mass here, and we get 0.1216 grams divided by moles, and we've set this up as in a gram to mole ratio, which is what molar mass is in grams per mole. So this should be 88.1 grams per mole. Once you practice these, they're pretty fun. We can try to convince you they're fun. In order for this technique to work, we must know whether the acid is monoprotic, diprotic, or polyprotic. Monoprotic is where you'd get a 1-to-1 ratio. Diprotic, in that previous example we looked at, 9.16, you get a 2-to-1 or 1-to-2 ratio. And then polyprotic, I mean, it could be 3 or 4, and then it would be triple or quadruple. And then, of course, the result would have been a molar mass twice as large, or 3 times or 4 times as large. So this wraps up chapter 9, and I did it in 2 parts. It's relatively long. There's a lot of different things going on with it, so just really be diligent with your studies as you practice these. Group them together. For example, we just went through the titration, so you could, practice all the titrations for a little bit and practice the activity series together and the oxidation numbers together. So the different concepts, practice those in a sitting and then take a break or come back rather than trying to combine it all together, because different parts of your brain are going to be worked out here. So I believe that's it for chapter 9. Thank you.